So section 5.2 is going to discuss binomial probabilities. Section 5.2. And I'm going to kind of get started here with something. This is not on your handout, and it's not something you need to really copy. I just kind of want to motivate the definition and what's going on here. So suppose you're going to flip a coin 4 times, and you want to look at the probability of getting, say, 2 heads. Now, I'm not necessarily guaranteeing that this is a fair coin, so the probability of a head, I'm just going to call P. The probability of a tails is going to be 1 minus P, or we'll call that Q. But, you know, it may be 50-50, maybe not. So, all right, this is all the things that can happen when you flip a coin 4 times. So what's that called, the list of all the things that can happen?
Sample space.
Excellent, that's our sample space. So we've got 4 events, each with 2 possibilities. So 2 times 2 times 2 times 2 is 16, or 16 points in our sample space. If I'm just interested in the probability that we get 2 heads, then that's these points in the sample space. Here, 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 here. So those are the different things that can happen that gives me 2 heads. But if I'm trying to calculate the probability, well, then that becomes a little bit more of a chore. So let's see about calculating that probability. And I'm just going to look at one of these events. For instance, the probability that you get a tail and then 2 heads and followed by another tail. Now, what happens on one flip, is that going to influence what happens on the next flip? If I flip a heads on the first one, should I necessarily flip a heads on the second one? No. So that means that these events are independent. And the probability of T and H and H and T, that can be broken up into the product of these probabilities. So write it like this. And because it doesn't matter what order I write them in, then maybe I'll put them together like this. That probability then is going to be P times P times P, or times Q times Q. Or in other words, P squared, Q squared. But that's just one way that this event can happen. How many ways are there that I can end up with 2 heads? I mean, it doesn't matter to me what order they come in. I just want to come up with 2 heads. So how many ways can that happen?
6.
Thank you. 6. There's 6 different ways that can happen. So the probability then of this event is going to be 6 times the probability of a head times the probability of a tail. That's our probability. Most likely, if it's a fair coin, these are each 1/2. That's fine. But this is the formula that we need to go through. It was a lot of work to get here. It's an awful lot of work. And in particular, we had to draw out the sample space to realize that we had 6 ways you could get the 2 heads and 2 tails. And that's kind of a drag, having to do all that work. It'd be nice if we could have something that would count these things for us. And that thing is the formula for a binomial probability. Now, you don't have to really know this, but let me show you all the little parts of this. Now, the notation here is a little different than what we use. So we'll do n choose k. Does anyone remember that? What's that for? Combinations. So this is the number of combinations of, you know, like k heads taken out of n flips times the probability of getting those k heads times the probability of the rest of them, and minus k are tails. And so that's what's called the binomial probability density function. Not a word that you necessarily need to know, but if you ever wanted to look it up, that's what it is. So the big question that we've got to answer and understand is, well, when is something a binomial random variable? So Nolan, what I'll do is I'll explain that with a little acronym here for us. Whether or not something's a binomial random variable depends on if it fits. So binomial random variable. There's several aspects as to whether or not something is a binomial random variable. First of all, you have to have a fixed number of trials. So in case you're curious, this is the part where you should be starting to take some notes. Fixed number of trials. And I stands for independent. The trials should be independent. And then there's T. There should be 2 outcomes for each procedure. And finally, each trial should have the same probability of success. So same probability of success throughout the trials. Now I chose these in a special order and in a special way. Can anyone see the little mnemonic device that I've created here for you? Fits. As you think about a process, an experiment, you want to decide if it fits. So we could look at a few examples. I could pick, say, 10 students in this classroom and try and figure out, well, what eye colors you have. Well, you don't have to look too far to realize that, all right, there's more than 2 possible eye colors. So that wouldn't lead to a binomial random variable. Something where the probability changes. Again, if I took this classroom and started deciding, well, sampling and seeing probability of getting a male or a female, that probability is going to change every time I take somebody out of the pool. So then that probability is going to change. All 4 of these things need to be present in order for it to be a binomial random experiment. Now, if it is a binomial random variable, then we can calculate these probabilities on Google Sheets. So hopefully you've surfed over to the link on D2L and opened up the link for our Google Sheet today. Kind of nicely worked out for us already. And let's see, I think it's right here. Here's your command for binomial random variables. Now there's really 2 commands, and I'll illustrate the second one in example B. But in example A, we're just going to get familiar with this command. I would kind of suggest that you use the first command pretty much exclusively. It's up to you how comfortable you are using the second command. The difference is that one's going to be cumulative and one's not. But let's take a look at example A. Assume that a procedure yields a binomial distribution with n equals 3 trials and a probability of success of p equals 0.3. Use the binomial table. Well, we're not going to do the binomial table. We're just going to work things on our own with Google Sheets. So we want to find the probability of success is exactly 1. So let's take a look here. Example A. There's a few things to take note of. N is 3. P is 0.3. And we want exactly 1 success. So things I want to take note of are right here. If I want to calculate this on Google Sheets, the format of the command is, of course, equals binom distribution. And I just got to double check it for myself real quick. I always mix up the 2 of these. It's going to be your X, then your N, then your P, and then false. that's what we're going to have to put in. In this particular case, it's going to be binomial distribution. X is 1, N is 3, P is 0.5, or no, it's going to be 0.3, and then false. So let's put that in and see what happens. See what kind of probability we get. What's the chance of getting one of these out of 3 if your probability of success is 0.3? And I hope that you follow along and do that. In fact, binomial distribution. Let's see, 1, 3, 0.3, false. So what probability are you getting?
0.441.
All right, sounds good. So you should be getting about 0.441. Great, great. That's exactly what we're hoping to get. Let's keep going with some more here. And move on to example B.
How do we write how do you want us to write the answer?
All right, good question. So probability that x equal 1 is 0.441. Thank you. So moving on down to example B, it says, assume that random guesses are made for 8 multiple choice questions on an SAT test. So there are 8 trials, each with a probability of success of given by 0.4. That doesn't sound right. It sounds like there's like 2 right answers out of 5. But let's see if that passes our test for being a binomial random experiment. So this is example B. First things first, is there a fixed number of trials?
8. Yes.
Yeah, n equals 8. Are they independent?
Yeah.
They are. Why are they independent though? Why are they independent?
What right does it affect if you're gonna get the next one right or wrong? Or
Yeah, if you guessed the first one right, it's not going to influence if you get the second one right or the third one right. It's just a lucky guess the first time. It's not going to affect the probability of guessing right the second time. Awesome. Thanks, Deanna. So they're independent. We got that. Are there 2 outcomes? What do you think? What are the 2 outcomes?
right or wrong?
Yeah, you got it right or wrong. And the same probability of success throughout the trials? Yeah, it's 0.4. So presumably they have 2 correct answers out of the 5 that are there. That will give you your 0.4 probability of guessing correctly, but the bottom line is that it fits. So this is a binomial random variable. We can apply our binomial probabilities, so great. Let's calculate that on our sheet. Actually, let's look at the rest of the problem. It says, find the probability that the number of correct answers is fewer than 4. So let me write that this way. I want the probability of x. What symbol should I use between these two? If x is, or the number of successes is fewer than 4.
Yes. What's that in a line under it?
Do I want the line under it?
Because that means equal to 4 also.
Yeah, the line under it would mean equal to. So now can I have 3.5 correct yeses? Can I have 3.7 correct yeses? No, it's discrete, right? So effectively, this would be P of X is less than or equal to, can anyone fill that in? 3. Well done. Yeah, basically it's like, all right, up to 3, we're okay, as long as we don't get the 4. Let's go over to Google Sheets here. For the probability, I've already typed in for you all this stuff over here. I've got all the different things that can happen when you're trying to guess on 8 problems. The one that's easiest to forget is that you might not get any of them right. You could guess them all wrong, so you would have 0 right. So your probability distribution should have this. Let's calculate the first probability here. So what was the command for that? Equals binom dist. By the time you get to the D, it should fill things out for you. You want X first, that is the number correct. So this time, instead of typing in a number, I'm going to type in the cell. I'm going to just click that cell. So that's the number of successes, followed by N. What's N for us in this case? 8. And the probability of success is 0.4, comma, false. So there's your command. Binomial distribution of A13, comma, 8, comma, 0.4, comma, false. So is there a good chance you're going to miss out on all 8 of your guesses? Is that very likely? What do you think? No, it's looking like you're at least going to get 1, hopefully. Now I need to repeat that for the second one and the third one, all the way down to the 8th one. But that's kind of a long command to type in. Can anyone think of something else I might be able to do to make my life a little bit easier here?
Drag it all this.
You can drag it down.
Drag it down. That's the reason that I chose to not type in the number itself, but I chose to type in this cell. So I can drag that all the way down. By the way, when I drag it all the way down, what should the total of this column equal? 1. Good. Because it's a probability distribution. So beautiful. Exactly 1. So everyone got the probability distribution here. Aiden, something not working out?
Yeah, I'm just trying to use
Let's see if we can't answer the problem. So the problem was to figure out, well, what's the probability of, let's see, let me do it over here maybe. Probability that X is less than 4. What am I going to do to figure out the probability that X is less than 4? Well, what events? Yeah, go ahead.
add the probabilities of 0 to 4.
Very close.
Times it.
Not add the probabilities of 0 to 4, but add the probabilities of 0 to
Oh,
Yeah.
3. Yeah, I want to go up to 3 here, right? Because I need the probabilities of less than 4, which is kind of a crucial detail. So, all right, get out your calculators and start typing in some numbers. I'm just kidding. Andrew, shame on you for reaching for your calculator. This is Google Sheets. We don't do that kind of menial task anymore. If I wanted to add up these 4 numbers, I can do it this way. Equals sum. And then just do what? Click and drag. I want these 4 numbers. And bam. You should get something a little bit less than 60%. Jackson?
How did you drag 1 through 8?
So initially I got this one and I just grabbed that little square in the right-hand corner and I pulled it all the way down. And that gave me all those problems.
Do for the less than 4.
For the less than 4, I clicked and I clicked this sum. So I clicked and dragged over 0 to 3. We don't want to include 4 because 4 is not less than 4. If it was a less than or equal to, if it was at most 4, that would be different. If it was at most 4, then I could include 4, but I can't. Are we okay with this probability? Now, I wouldn't worry about this second part of the command if you're not really comfortable with it. But let me show you what happens with this if you use true. And I've already got the first one written here for us. So all we need to do is drag this down. This doesn't look right. Oh, I think I have the wrong probability here, right? What's the probability for us? It was 0.4. There we go. So notice that it matches on the first one. The first one looks good. But when I drag down, here's what's happening. It's adding up all the probabilities less than or equal to this. So if you add up these two, you'll get this. If you add up these 3, you'll get this number. And in fact, here's a nice double check on our work. If you add up these 4, guess what you get? You get this number, which matches our calculation. So this is a cumulative density function. You know, and it adds up to 1 here at the end. That's what it should add up to. That's great. It's up to you if you want to use this or not. I mentioned it once with fear and trepidation in my heart, but I don't know. I think it's probably just as easy to use this. It's up to you what you feel comfortable with. So, in any case, the probability that x is less than 4 or at most 4 is 0.594. Comments on that one? Comments or thoughts? Morning.
We shouldn't use true unless we're trying to.
You know, and you're only going to use true if you're trying to accumulate these things. So that is, you have a total probability of everything less than or equal to this number. So this is everything less than or equal to 3. This is everything less than or equal to 4, and so on. So it does have its use, and if you're comfortable with it, that's great. For the most part, I'm just going to stick right here, and we'll just get what we need. We can get it directly by just adding up just the probabilities that we need. Let's keep going. Comments or questions on that one?
So you said we only use true if the total is less than or equal to the number?
You only use true if you really are comfortable with what that does. I would suggest that you just use false and then add up what you need. You need the probability that x is less than 4. Just sum up those probabilities that way. I think that's probably the safest way to do things. But again, it's what's in your comfort level. Anything else? Sam?
I was just gonna ask how you got a reading for that. Like,
Oh.
the probability, like the other.
Let's- So it asks us for the probability that x is less than 4. Let's take a look at which of these numbers satisfy less than 4. 0 is less than 4, so I'd want that one. 1's less than 4. Oops, didn't mean to do that. 2's less than 4. 3's less than 4. So all these are less than 4. But is 4 less than 4? 4 is not less than itself. 4 is not less than 4. So the only things that satisfy being less than 4 are these numbers, 0 to 3. So it does make a big difference, and it's something you have to pay attention to is the language here. We wanted at most, or excuse me, we wanted fewer than 4 successes. Now, had I typed in at most 4 successes, does that change things? I think it does. How does that change things? Can't be more than 4. It can't be more than 4, but what does it change?
The calculation is when you have to include 4.
Yeah. So basically, at most 4 successes includes 4. So you could have 4 successes, and that would be part of your probabilities then. So we can actually get that number right out of our table because it's right here. Basically, you're taking this number and adding 0.2322, so you get 0.826. So it's something to be aware of, is a little bit of the language there. At most, at least. Those are going to be things that include or have an equal to. Less than, more than, you're not going to have that equal to possibility. Let's move on to example C. Assume that when adults with smartphones are randomly selected, 61% of them use them in meetings or classes, except your stat class, right? Layla, you're supposed to nod at that and say, yeah. All right. If 6 adult smartphone users are randomly selected, find the probability that exactly 3 of them use their smartphones in meetings or classes. So let's think. Let's go through our little process here and decide if it fits. Do we have a fixed number of trials? No. I don't know.
Would it be no because of the randomly selected amount?
Well, randomly selected actually gives us the independence. Because if you're selecting people at random, then, what somebody picked at random does with their smartphone in a meeting or class really has no effect on what's going to happen with yours.
So would it be 3?
Well, there is a fixed number of trials here, but it's not 3.
There's a one trial?
6. 6. So there's six smartphone users, so that's a fixed number of trials. So yeah, n equals 6. Are they independent? We just discussed that. Yes. And that's because they're chosen at random. So what somebody that's not related to you or unknown to you does is not really going to affect what you do. Are there 2 outcomes?
Yes.
You either do or don't, right? So yes. And is the probability of success the same? Yeah, it's really by what's called your 5% rule. But the answer is yes. For practical purposes here, the probability is 61%. Okay. So we want to find the probability that exactly 3. Exactly 3 use their smartphone in classes or meetings. So, all right, that's going to be a binomial distribution problem. See if you can't fill it in and get that probability. What probability are you getting? 0.269. All right. So it should be 3, 6, 0.61. What's the last field here?
False.
False. Nice. Yay.
Is that because it has to be exactly 3 and it can't be?
Has to be exactly 3. If you put true there, then it would give you the probability that 3 used it, or 2 used it, or 1 used it, or none used it. It would give you the total probability of all those things less than or equal to 3, which is not exactly what we're looking for in this particular case. So that one would be false. 0.26928. All right, nice, nice. Let's try a similar one with a little bit of a twist. So that's going to be example D. Are we okay with example C?
So when you say exactly, they mean the same,
Yes.
right?
One more time when I said exactly.
When they say exactly 3, that's the same, right?
Yeah, exactly 3 means x equals 3, and that's it. Not higher, not lower, exactly 3.
I'm confused about typing in false and why you know this. What's that?
False just means just give me the probability here. Whereas the true, I wouldn't worry about it. I just keep it simple on yourself and use false.
Okay, and then the answer's false because it's, what's the,
No, the answer when you type in false, when you type in the command like this, the answer is just your probability. So it'd be 0.269. Oh, is there a follow-up question that maybe I to look? No, it says find the probability that exactly 3 of them use their smartphones in meetings or classes. So
okay.
yeah, that probability would just be 0.269. You okay with that then?
Yeah.
So
All right.
you can do false every time then.
Yeah, I would just stick to false. I mean, I always struggle every semester with, should I even mention true? I did this semester, and other semesters I haven't. Trying to decide if I'm regretting it already. But I think the easiest thing to use is just use false and then just add up what you need. Probably works out pretty good. Okay, let's move on down to example D, which is pretty similar. It says, assume that when adults with smartphones are randomly selected, 59% of them use them in meetings or classes. If 11 adults smartphone users are randomly selected, find the probability that fewer than 4 of them use their smartphones in meetings or classes. So, okay. Well, we've already been through this procedure once with example C. It is a binomial random variable. We've already done the fifth thing. So let's get down to the probability that we need to calculate. So this is example D. I know that P equals 0.59. N is what? What's N for us in this case? N is 11. Good. And how would you characterize the probability that we're looking for? Probability that, what's true about X?
Less than or equal to 3.
All right, less than or equal to 3, that works. It's less than 4, or because this doesn't include 4, I could say, well, it's less than or equal to 3. Either way, it's up to you. So I've got the table of all these probabilities set up for you a little bit. We've got to type it in here. Equals binomial distribution. I want X. What should I type in for my X here? What do you think?
You select the cell.
Yeah, let's select the cell right here. Nicely done. Select the cell, and then it's 11 is our fixed number of trials. Probability of success is 0.59. And then we're going to stick with false. So that's how your command should look for that first cell. And I asked you, well, do you want me to fill out the rest of the way? Sure, why not? And do my work for me, I appreciate it. Let me go back and, if I was looking at that going, boy, that looks kind of weird, how could I feel a little bit better or prove that this at least seems right?
Add it up.
Yeah, what should it add up
Sure is
to?
one.
Should add up to 1. And we nailed it. It adds up to exactly 1, which is a good thing. Now, if you're looking at too many digits and you don't want to look at all those digits, then you can decrease the decimal. So I don't want to look at quite so many digits, so I'll just dial it down a little bit.
How do you do that?
It's up here, there's a little arrow next to the 0. So, yeah, if you're getting too many digits, driving you crazy, I don't blame you. Just look at a few of them. Now, I want to find the probability that x is less than or equal to 3. So I can do that with a sum command, equals sum. And let's just pick up the variables or the values that I want. Yep. So you type in sum, then you click and drag the probabilities that you want. 0 to 3, and bam. Now, I don't want it to autofill here. All I'd want is the 1. So,
Can you try that again, how you did that?
sure. So let me do that. You type in sum, and then you highlight just the probabilities that you want. So that'd be 0 through 3. And then it grabs the cell numbers here. And out of compulsion, I'm going to put that right parenthesis there. You don't really need to. Google will fill it in for you. And just press enter. Should give you about 3%. Bless you. You guys able to get that 3 there? 3%? All right, pretty good. So 0.0342, etc. All right, nice, nice. Let's keep rolling. Let's try example E. A survey showed that 72% of adults need correction, that is eyeglasses, contacts, surgery, etc., for their eyesight. If 22 adults are randomly selected, find the probability that at least 21 of them need correction for their eyesight. Is 21 significantly high or significantly low number of adults requiring eyesight correction? Well, all right, let's see here. Example E. First things first, is there a fixed number of trials?
22.
Yeah, n equals 22. Are they independent? Yeah. If somebody's chosen at random, what's happening with their eyes is not going to impact your eyes. Are there 2 outcomes? What are they?
Correction or they don't.
Yeah, you need it or you don't. And they're technically dependent events, but we can consider them independent because this is such a small sample. So the same probability of success applies throughout the experiment. And that probability is 0.72. So yeah, P equals 0.72. All right, so it fits. Yay, happy about that. We want the probability that at least 21 out of the 22 adults require surgery, or I'd say correction, I should say. So as a probability, what should I write? P of X. What's the probability involved here?
Alright, 21.
Greater than or equal to 21. At least.
Oh, yeah, it's not at most.
Yeah, it's not at most. At most would have this turned the other way, right? That'd be less than or equal to 21. This is at least 21. Is 21 a significantly high number of adults? That's going to depend on the probability that we get. What's the cutoff for a significantly high or low event? What percentage? Remember?
5%.
5%. So let's see if this is less than 5% or not. If it is, then it's significantly high. If it's not, then it's not. So let's go over to Google Sheets. And let's see. This is example E, so let me click over here. You've got two probabilities to calculate. X equal 21 and X equal 22, because it's at least that much. So equals binomial distribution, not distribution, X, that's going to be this. You don't have to type in this column like this. You can just type in 21 and then 22, 21 comma 22, and then the probability, which was 0.72, and then false. And it's asking me, do you want to repeat it? Yeah, sure, but I need to go back here and change that 21 to a 22. So I didn't actually use these, at least directly. But I'm not done yet. How am I going to get my answer?
You add them together.
Yeah, add them together. Nick, what do we got to do to add them together? What would you suggest?
Just do the sum of both of them.
Yeah, just do the sum command. So I'll sum, highlight both of these. I should get about 7%. Okay, do I want to autofill here? No. All I wanted was this one. So the probability is about 7%, or 0.7% really. 0.0069.
So when you did the sum thing again,
So the sum thing, let me click there and then click here. It's kind of cool when you're working in Google Sheets. If you click the cells that you have inside your command, it'll highlight what cells you're using. So you can kind of look back and say, oh, it's highlighting these two, it's summing those two, that looks good, that's what I wanted. So it's a double check on your work.
We're not getting, one when we sum those because it's not like 0 through 22, right?
Correct, we're not summing all of them, we're just summing up two of them. Yeah. So you're exactly right. Now in the next example, I actually did create the distribution for the entire function. But before I get there, let me look here. Are we okay with example E?
Can I see what you put in cell
Number 4. The only difference between cell 3 and cell 4 was I took the number of successes here, that X, and changed it to 22. Now,
Different song.
Have to add them up to get that, or couldn't you just look at what 22 is?
no, because you have to include the probability of 21 as well, right?
Yeah.
All right. Somebody was, Jess, were you getting something different still?
Hold on. You're talking me or?
Either one. I mean,
No, I figured out what I did wrong, sorry.
got it?
Yeah.
Okay.
Can I also see what you put in cell
C3, right there. It's just adding up those two. Okay. Let's move on down to example F. And I'm going to add a little bit to this whole discussion. So, assume that different groups of couples use a particular method of gender selection and each group gives birth to one baby. The method is designed to increase the likelihood that each baby will be a girl, but assume the method has no effect. That is, the probability of a girl is 0.5. Assume that groups consist of 46 couples. Complete parts A through C below. So part A says find the mean and standard deviation for the number of girls in groups of 46 births. All right, well, this is really practicing stuff that we did in section 5.1, and I'm happy to do that. Remember what we did in section 5.1 to try and find the mean. By the way, what other names did I give the mean of a probability distribution? I gave a couple of them. The average, what else? Mu, and one more. The expected value. So the expected value is what you typically expect when you run this experiment. Now, before we get there, what would you expect? If you have 46 kids and there's a 50-50 chance of a boy or a girl, how many girls do you expect out of the 46?
Around 23.
Yeah, 23, right? Looks pretty easy. Do you remember what we did to calculate that expected value? We took x times p of x, so that's this column right here. What did I do after I took x times p of x to get the expected value?
Summed it up.
I summed it all up. And guess what? It's 23. Wow, that's kind of cool. That's going to give us a shortcut. To find the standard deviation, you first had to find the variance through this calculation. You took p of x times x minus mu, squared it, add all that up, and that gave me the variance. And then I need to find the standard deviation. How do I find the standard deviation once I've got the variance?
Square root of the variance.
Yeah, it's square root of the variance. So I could do equals SQRT of this, and bam. No, I don't want an autofill there. So great. And here's a reminder. This number, that's your mu, that's your expected value, that's the average. That's what you typically expect to happen when you do this experiment. So here's our mean, here's our standard deviation. And if you're looking at that and going, well, did we really have to do all that work here to get the mean? The answer is no. Let me share with you something a little bit more about binomial random variables. But the important thing is that it only works for binomial random variables. The problem that I have on exams with this is that people use this for everything, even when it's not a binomial random variable. It only works here. So if x is a binomial random variable with n trials and probability of success equals p, then two things are going to happen. First of all, the mean, what's our symbol for the mean? Does anyone remember? Mu. Perfect. Mu, it's a Greek letter. The mean is simply n times p, which is what you calculated a while ago. The standard deviation, well, let me do it this way. The variance, sigma squared, is n times p times 1 minus p, or n times p times q, as long as q means 1 minus p. The standard deviation, that's just sigma, not sigma squared. Can anyone tell me what that was going to be? So to get from here to here, I have to take the square root. So, boy, that's a lot easier than working with the rest of these things, with doing all that work for the formula.
What's that say at
standard deviation,
For the variance where it says
or n times p times q. A lot of times, so p is the probability of success, then probability of failure. If p is your probability of success, your probability of failure is 1 minus p. And sometimes we'll call that q, just for convenience. So that's where the q is coming in. It's going to depend on the book and the source as to whether or not they write it with P or Q, but they mean the same thing. So how does that apply in this particular case? Well, good question. Let's just kind of double check things here. So n for us was 46, P was equal to 23. Let's use these to find the mean and the standard deviation. Well, I'll find the variance and then I'll find the standard deviation. So the mean is going to be 46 times 0.5, which is 23. We've already seen that that one works. How about the standard deviation? Well, that's n, which is 46, times p, which is 0.5, times 1 minus 0.5.
Wait, that's the variance, right?
The variance, should say. Yeah, thank you. So that's 46 times 0.5 times 0.5 again. And that should give me, what, 11.5? Somebody double check me on that one. Oh. What's wrong here? How come I'm getting 15.5? 23 divided by 2 is 11.5, isn't it? 46 times 0.25, 11.25. What's wrong here? Okay. Things were going along real nice until now. This looks... Question?
Oh, we did
X
one.
minus
What
mu.
did we have to do 23 times?
X minus mu times p of x squared. Now this looks right. So something looks wrong with my formulas, because the formula I have on Google Sheets should match this one, which would be 23 over 2.
That's what I did. I just didn't write it as like parentheses 1 minus 0.5. I just wrote it as 0.5.
Yeah, 0.5 times 0.5 is 0.25 times 46. Oh, I typed in a 45 here. All right, that's part of the problem. 46 times 0.25, still low. 11.5 doesn't match what I have here on Google Sheets, and I'm trying to figure out what's wrong. I guess of the two of these, I don't trust this one. There's something wrong here. I'm not sure what it is. Let's see about that formula again. So it's probability, which is in column B, times your x minus the mean is 23, and then square it. So that looks good. And sum it all up. That's way off. I'm not sure what's going wrong there. Okay, well, that's a problem I'm gonna have to figure out later. I'm not sure what's going wrong there, but I do trust our calculation here.
So Professor,
Yeah.
I am deleting all the ones below cell 10. and then just drag cell time down, cause I changed that and I got 11.5.
Did you?
Yeah,
Oh,
cause I think it's
oh, let's, you know what?
not aligned, it looks like B19 times A21 minus 23.
Yeah, okay. So let me just copy this one and drag it all the way down.
Yeah, I was thinking about 11.5.
And now I need the total, so I'll copy that and paste it over here. Still not. All right, let me try it all the way from the top. There we go. Ah, beautiful. Thank you so much. 11.5, cool. My faith in this has been restored. And then equals, if I want the standard deviation, I can do the square root of what I have up above. So there you go. So if you wanted to fix yours, then what you got to do is, or the easiest thing to do is go up to the top here, click, and then drag that square all the way down to the bottom. It should give you the 11.5 that we knew it would. All right, so the square root of that is about 3.39. And that's what I was looking for, is that square root. Yes?
So instead of doing all the math for the variance, can we just do
The formula?
divided by 2?
Well, so if you're trying to calculate this for me on an exam, I would expect you to use the formulas. I only showed you that on Google Sheets as kind of a reminder and practice of stuff that we did in 5.1. But no, I don't expect you to do it the long way. I sincerely hope for these problems you do it exactly the way I did here. So, is that answering your question? Yeah, there's no reason to do it the long way. But that is only part of the problem that we've got here. It says use the range rule of thumb to find the values separating results that are significantly low or significantly high. So the range rule of thumb says that our typical values are going to lie within 2 standard deviations of the mean. So according to the range rule of thumb, I want to calculate this sigma minus, or mu minus 2 sigma to mu plus 2 sigma. So I know the mean is 23 minus 2 times the standard deviation. Standard deviation was 3.39. 3.39. And then I want to do that on the other end of things. I want to go 23 plus 2 times 3.39. So Andrew, don't break out your calculator on this one. We're going to use Google Sheets to make our life a little bit simpler. Let me go back to the sheets here. And let's see. Yeah, I'll put it down at the bottom. I want to do, now I'm going to just type in a description of the command. It's going to be mu minus 2 times sigma, and then mu plus 2 times sigma. So I'm just giving it some labels, but that's going to equal, see, I'm being even lazier. I'm not even typing in mu. Mu minus 2 times, where's the times key for Google Sheets?
Asterisk.
The asterisk, shift 8, times, and then I'll click the standard deviation. So that's on the low end. Let's figure out what it is on the high end, equals mu, which is 23. This time I'm just going to type in the 23 plus 2 times sigma. Bam. That's what separates my low and high values. Can you show the formula again?
Let's help.
This stuff here, that what you're looking for? Okay. So I want to try and draw this and help you understand our little cutoffs here. So what was this? This was like 16 point something. Somebody's still on that page?
16.217.
And the other one?
29.782.
Okay. So let's see, let's go down to 30, 29, 28. So I want to determine what events are unusual and what events are more typical. So here's the cutoff. The cutoff is 16.217. And on the other end, it's 29.782. So what events would you list as the unusually low? And this would be unusually high. My point in doing this is I want you to include the right numbers. What about 16? Is 16 going to be unusually low? Yes or no?
Yeah.
Get a nod from Larry and a few other people, yes? Yeah. All of these are your unusually low events. How about 30? Is 30 unusually high?
Yeah.
Yes.
Yep. Now, it's true that you can't actually get these numbers. You can't actually get 16.217 girls. That's okay. It's still helping you identify where the cutoff is. And so if that cutoff doesn't include 16, it doesn't. And in this case, 16 would be unusually low. Are we okay with that part? This is something that would be like a good test question, is to use the range rule of thumb to help identify the unusually high and the unusually low values here.
Is there a name, like the middle part?
You know, I struggle with that sometimes. I call these typical values. I don't know as though there's a actual name for the middle part. So we can call it Deanna's forgotten numbers if you'd like. Yeah. No, you're shaking your head. No, thanks. Yeah, Aiden?
So do you want us to draw this on a test or should we?
No, you don't have to. I just drew it out to make it very visual and hopefully make it a little bit easier to understand. Is that we're not including, or we're including 30 and we're including 16. Everything above and everything below.
So if we were answering on the test, will we write 16.217, comma, 29.782?
I guess it depends on what I'm asking, but if I was asking for what are the unusually low values, you'd say 16 or less.
Yeah.
And for the unusually high, 30 or more. And of course, there's a variety of ways you could do that, but whichever ones works for you. Go ahead.
How about the problem we're working on right now?
So let's take a look back. I think they're going to ask us about one event in particular. Does the result of 33 girls, is the result of 33 girls a result that is significantly high? What does that suggest about the effectiveness of the method? So what do you think? Is 33 girls unusually high?
Yes.
Absolutely, yeah. So does the method seem to be effective? Yeah, it really does. In fact, if you start looking at the probabilities of getting 33 girls or more, it's pretty small. I mean, 33 or more, that's a pretty small probability. Yeah, might be close to 5%, but it's definitely on the unusual side. Yeah, there's a question over here.
So for the previous one, if I just answered that question for significantly high or low, can I just put like the greater than or less than symbol and put
Yeah.
that value?
Yeah, I think that's what Aiden was asking. So unusually low, you could say X is less than or equal to 16. Unusually high, you could say x is greater than or equal to 30.
Okay.
So you can just write it out, just say it like.
Yeah, you could do that too. You could just say it's at most 16 or at least 30. So that would be yet another way you can say that. So at most 16 and at least 30. Yeah, well done, well done. Okay, let's see where we're at here. Example. I think I'm gonna pause things here, gonna break this video up into 2 videos. So we'll do another part coming up.